Hello and welcome to the session where we are going to look at multilinear regression in our analytics ScratchPad. So to begin with, we're going to look at an equation of this form. So there's some output variable y, and it's equal to a polynomial function. So it's going to be equal to, let's just arbitrarily choose 3 plus 2x plus, and let's say 5x squared, and just to make it a bit more fun, let's say 4 times the square root of x. So that's the function that we want to fit. And our first tendency will be to say that, well, this is nonlinear because of the x squared and the square root of x. But what we are fitting in multilinear fitting most of the time are the parameters in front. And you see here that this equation is linear with respect to these parameters. And another way to write this would be to say y equals, and let's call these constants k1, well, really, let's call it k0 and k1, k2, and k3. So we have some set of data. We have a set of data given to us as y of x, and we suspect this kind of form, and we would like to fit these constants to that form. So we are going to use multilinear regression to do that. And in fact, that should be the default always. We should always be trying to fit using multilinear regression, and we only go to nonlinear fitting as a last resort. And that's because in multilinear regression, there is just one solution. It's not a search in a space, in a 4-dimensional space like we have here. There is one solution. So given a set of data, there is only one solution, and that is the optimal solution, globally optimal. Whenever we do nonlinear regression, then it's always going to be a local minimum. So linear regression is really the optimal way to fit anything, and it's only when the system is strongly nonlinear with respect to what we are trying to fit that we have to resort to nonlinear regression. So let's look at that in the context of our analytics ScratchPad. And we are going to generate a data set. So under data source, we have prepared here a function which does that. So let's just have a look at that. So you can see here that we are going to generate 200 rows. So I is the index of the rows, and we're going to divide it by 100 so that x varies just between 0 and 2. And there are many, there's a fairly high resolution of 200 between that 0 and 2. And the equation we described just now, well, I've used different constants. So I've used here 5 plus 3 times x plus 2 times x squared plus 7 times the square root of x. So let's go ahead and generate this data set. And by the way, you see here that we only have 3 columns, I, x, and y. So we don't have any of the other features that we don't have the polynomial terms there. So let's just generate that quickly. So we can see I, x, and y, and you can see how y is varying with respect to x and so on. So let's now, let's try to work in a form that's friendly towards this. So to regress this, we will need a column of data for each of these terms. So we need a column of x's, a column of x squareds, and a column of square root of x. We also need a column of ones here. So let's create that. So we head over to our table editor, and we can simply define here, we know this is going to be the row object. So row object, and I'm going to call x0 the 1, and row object, let's call x1, that's going to be x itself. So remember, in our table, we have stored the values as x's over there. And then for x squared, so I'll call this x2 equals, and let's just say it's going to be this times itself for x squared. And then we need the square root as well. So let's call, let's say row object square root of x equals r obj dot x, and we have to use a math function, math dot sqrt. Oops. Math dot sqrt. And that's it. That should generate for us the extra columns. So we should save this in a new table. So let's call this putting data and apply that, right? And so we have the columns we are looking for. It's a little bit hard to see on here because there's a little bit of overwriting, but it looks like we have the columns we are looking for. So now to fit this, we head over to analytics, and we want to do this on table on fitting data. That's the right table. And field needs to be our output variable. So we are trying to fit this to y, and then the terms we are trying to fit are these ones. So we'll remove I, x, and y, and we are trying to fit against x naught as being our constant, x1 for x, x2 for x squared, and the square root of x. And we can ignore the other things. So when we click on linear regression, it's just going to look up the table that we are going to use, the table of data. It's going to look up the output variable and the input variables. And let's save this result as with parameters. And let's just do linear regression. And so we can see it's done that very quickly. And if you look at these values, right, this is approximately 5, this is approximately 3, 2, and 7. So 5, 3, 2, and 7. And those are the parameters that we used to generate that data. So from this alone, we can see that it has worked. It has fit the data correctly. Of course, we'd like to verify that just by looking at the data. And so we can do that by using the fit, by using these parameters to generate our data set, to add a column to our data. So to do that, we select parameters as being fit parameters, and we set the field as y. Well, that's all. So you just select fit parameters, because in fit parameters, it's also recorded that the fields that we use were these ones, and that the output field was the y. So all we need to do to use the fit to actually generate the values is specify parameters here. So even if we choose the wrong values out here, that won't matter because it's just going to read from here. So we select fit parameters, and then let's save this result as results. And let's click on linreg fit. Okay, and if you untwirl this, you can see we now have a new variable, y predicted. So there's the predicted value of y, and there's the original value of y. There is a very slight difference between the two, but that's many decimals into it. So to actually check that it is giving us a reasonable fit, let's go ahead and plot this. So if we head on over to data document, and let's say we select data tables, and in our data table, we want a scatter plot using just markers, not lines and markers. And in the output fields, let's use the predicted value. And for the input field, let's use y. So we are plotting y against itself. So we are expecting to see a nice straight line where basically the x value of that plot is equal to the y value of the plot, where the x value is y and the y value is y pred. Okay, so let's save that output as results plot, and we click plot. So that plot is not going to the workspace, that will go to this part called document. And if you look at this line as you travel along it, you can see this is basically a parity plot. And yes, we are getting a very good fit here. So that verifies to us that our linear regression fitting has worked fairly well. Thanks for listening.